How you doing? I'm Mr. Rose, and today we're going to continue our discussion on momentum, specifically conservation of momentum. Thus far, we have spoken about one type of interaction, which I deem an explosion. An explosion is when we have seemingly one object, some type of interaction, like an explosion, and it bursts into more than one, two, three, four, etc. And as a quick review, what we need to do is we need to add all of the momentum in the y direction, add up all the momentums in the x direction, and we should come out to however much momentum we started with is the same amount of momentum we're going to end with. What we're going to be discussing today are two different types of interactions, an elastic and an inelastic collision. An elastic collision is when we have two or more objects collide and bounce off each other. When a collision is 100% elastic, it does help us out a little bit because we can use either conservation of momentum, conservation of energy, or both in the same problem. The other type of interaction is an inelastic collision. So when we have two or more objects collide, and those two objects collide and stick together. Now in an inelastic collision, although energy is conserved, it is much more difficult to use conservation of energy. This being is in that collision, there's always some kind of loss, so to speak, of energy, or energy that transfers into the system. So when things deform, when they stick together, we lose energy in things like heat, sound, friction, and it's not always easy to account for that. So I have two examples written out in the scheme of our super technology. This is a piece of paper with a question. Get very close. Please read that question, and the picture goes with that question. Now, the 30 centimeters that I have in this diagram is relatively useless. It's trivial information. We don't need it based on the given information. What we're essentially looking for is we have mass A colliding into mass B. I want to know the velocity of mass A just before the impact. Then I want to know the velocity of mass A and of mass B after the impact. This would be an example of a perfectly elastic collision. The second question is an inelastic collision. This is with a collision and a car and a moose. Several years ago in Watertown, you may recall there was a moose running through the streets. So here we have a car driving through the town of Watertown, collides with that moose, and the moose goes straight into the windshield, into the car, deeming it an inelastic collision. So now that you've hopefully read both of these questions, what I'd like you to do is take a pause, give an attempt to solve each of those questions. Once you're done with that, come on back and let's check to see how you did. Hi, welcome back. Now let's see how we did. The first part of this first problem with mass A swinging into mass B is relatively trivial. I told you that we are we're starting at some height. We raised the ball up some height, and I believe it was 0.08 meters. So I can use straight conservation of energy only looking at mass A. Mass A has zero potential energy. I bring it all the way up to the top. So I'm going to use my my total energy initial equals my total energy final, my kinetic energy plus my potential energy plus work, and that work is outside energy, friction, heat, etc., equals my total energy after, kinetic plus potential. Now again, we said it was perfectly elastic. Perfectly elastic meaning I have no work. That can cancel out. As I lifted through that potential energy, started at rest, therefore there's no kinetic energy. That cancels out. Same thing after, at that impact, it's transferred all of its kinetic energy all of its potential energy into kinetic energy. Thus, there's no potential energy at the bottom. So I'm left with very simply mgh, my initial condition, equals 1/2 mv squared, where this is the velocity of mass A. I know my masses cancel out because it's the same mass. I'm left with the velocity of the square root of 2 times g times h. And throwing in my numbers, I get a velocity of 1.25 meters per second. So what that means is the mass A is moving at 1.25 meters per second. That moment it strikes into mass B, sending mass B flying. What happens there is this inelastic collision. B is going to go that way. A should swing backwards a little bit. It's possible that A will continue. We'll find that out at the end. So now I'm going to use my conservation of momentum. Conservation of momentum, very simple. All of my momentum, my closed system before is equal to all of my momentum in that closed system after. So I write out, here's the momentum, my mass and velocity initial of A, my mass and initial velocity of B. I know B was just hanging there. That cancels out. After the collision, I don't know a whole lot of information. Maybe mass A does stop. Maybe mass A again continues on, maybe mass A bounces back. So I can't just cancel anything out arbitrarily here, like I could here where I knew velocity B was at rest. So now I have my initial condition of mass A and my velocity A to start has to equal the final velocity, mass A, velocity A, after, plus mass B times velocity B, again, after that collision. Rearrange my variables. I just want to bring everything I know about A to one side, everything I know about B to one side. I know mass A, that was given. I found my initial velocity, A, V naught A. I don't know my final velocity of A after they collide. I know mass B. I don't know my final velocity B. So I have one equation with two unknowns, velocity A and velocity B. So it's kind of stuck here, except again, remember, if it is perfectly elastic, like I said, we can utilize conservation of energy. Utilizing conservation of energy, I know 1/2 mv squared. Now this v initial squared is that moment just before it strikes mass B. Again, I didn't even include mass B here because I knew from earlier it started at rest. No kinetic energy. Equals the kinetic energy just after impact, meaning all of that kinetic energy, now bang, that moment after the collision, both of those are moving with their maximum kinetic energies individually, 1/2 mva squared plus 1/2 mvb squared, where va and vb are my final velocities after the collision. Rearrange that again by bringing all of my, separating my variables, everything I know about mass A on one side, everything I know about mass B on the other side, and again I'm left with two unknowns, va and vb. Well, we know from simple algebra, if I have two equations and two unknowns, I can solve, and solving those equations out, I should have velocity A of negative 0.537 meters per second, velocity B of positive 0.85 meters per second. So velocity B, that ball keeps going one way. When A knocks into it, A is going to get ricocheted back. So that's how we solve that elastic collision. Let's move on to the Moose question. The Moose vehicle car accident. This, I said, was an inelastic collision. In elastic collisions, we have to utilize only conservation of momentum. Now, this question asks how much energy is being lost. So I chose this to show that in these inelastic collisions, we're going to lose energy. So my conservation of momentum, my initial mass of the car, my initial velocity of the car, my initial mass of the moose, my initial velocity of the moose. They're stuck together. So here where I have mt vt, I could have written mass of the car plus mass of the moose, but I just know that's the total. I know that the moose starts at rest from my initial condition, so I can rearrange to find my final velocity of the car and the moose is the mass of the car times the initial velocity of the car divided by that now whole system, the mass of the moose plus the mass of the car. So this is my velocity of everybody traveling together. I need to find out their initial and their final kinetic energies so I know how much energy we lose in that collision. That's what I started to do over here. My initial condition, well, that's easy. My initial condition, the moose isn't going anywhere. So 1/2 mv squared, that's 0. My initial kinetic energy is just the kinetic energy of my car, 1/2 mv squared. My final condition is a little bit more complicated, but it's just some algebra. My final condition is the kinetic energy is 1/2 mass of the car times the mass of the moose. That is the system together, plus that total velocity together. Well, I know this Vt, I just solved that using conservation of momentum. So my total velocity is just the mass of the car times the velocity of the car, initial condition, divided by the total mass. That's the velocity after. Simple substitution, and now maybe I start to recognize things to simplify. This is why we do things in terms of variables. I can cancel out my mass here. I'm sorry, before I cancel out, I'm going to separate this out. In other words, bring through my squared. 1/2 m car m moose, nothing happens to that. Bring through my squared, mass squared of the car, velocity squared of the car, and I have two mass totals. Well, wait a second. That mass total is just this. One of those cancels out. One of those cancels out. My kinetic energy final is now just 1/2 m mass of the car squared, velocity initial of the car squared, times the total system, my moose and my car. Well, if I start to recognize, wait a second, kinetic energy initial, 1/2 m initial v squared. Well, let's see, I have the velocity of a car. I'm sorry, this should be a car. I have the mass of my car, I have the velocity of a car, kind of looks the same. I can pull out a 1/2 m car, v naught squared. This is my initial kinetic energy. So my kinetic energy final is just my initial kinetic energy times the mass of the car divided by the total mass of the system. That makes sense. It should be some fraction of that kinetic energy. So now to find my percent energy loss, I still haven't plugged in a number. I haven't used one number yet. To find my percentage of energy loss, well, this is just 10th grade algebra. My percent is my final minus my initial divided by my initial, my maximum, times 100. Well, my final is my kinetic energy, initial kinetic energy, times the mass of the car, times the total mass of the system, rather, divided by that total mass of the system, minus my initial kinetic energy, divided by my initial kinetic energy, and all of a sudden, everything is canceling out. I'm losing a lot of variables, which makes my life a little bit easier. I'm left with some negative mass of my car, minus 1, divided by the total mass of my system, times 100. That all should come out to about 33% energy loss in the collision. This is an example of why you cannot use conservation of energy for an inelastic collision. Hopefully you did well. Please bring questions to class. If you have anything, like, click, and or subscribe. Thanks for paying attention a little bit today, and I will see you next time.